So the next discrete structure that we're going to talk about are integers. And integers are a foundational discrete object. There is a branch of mathematics called numbers theory that is nothing but the study of integers. So we're going to, we know that integers are just whole numbers, and we're going to find out that integers also have properties and operations just like sets and sequences. One of the operations that I can perform on an integer or a series of integers is division. So if I have some integer a and some integer b, I can perform division on them. So let's say that I were to take a and I were to divide it by b. It is going to give me some quotient and it is going to give me a remainder. Let's see what this looks like. Let's say, for instance, that a is 14 and that b is 7. I can take 14 and I can divide it by 7. I'm pretty sure that the quotient is 2, and I'm pretty sure that the remainder here is 0 because that would be evenly divisible. What if I took the integer 15 and b was 7? Now when I take 15 and I divide it by 7, I have the quotient of 2, but this time there is a remainder of 1. The division algorithm tells me that the value of a can be expressed uniquely in terms of d by this following equation. And the equation is the value of a is some kind of a representation of the value of b multiplied by a quotient plus a remainder. So let's look at my value of a. When a was 14 and when b was 7, we say that 14 is equal to 7, and my quotient is going to be 2 plus a remainder of 0. If I were to look at my second value, a equal to 15 and b equal to 7, I say that 15 can equal my value of b multiplied by 2 plus the remainder of 1. I'm getting these two from the division that I just did. Now, it may be obvious to me when I'm using 14s and 7s, but sometimes I'm given a value of a and b where it's not so easy to determine what the q value and the r value is for this equation. So what I really need is some kind of a formula that allows me to calculate q and to calculate r. So we're going to find out that the quotient is going to equal a divided by b, and that the remainder is going to equal a mod b. Let's try it with my original two values, 14 and 7. So if I want to find out what my q is, I'm going to take 14 and I'm going to divide it by, or 14 divided by 7 is going to give me 2. If I want to know what the remainder is, I'm going to take 14 mod 7, and this is going to give me a remainder of 0. So that was the equation that we had, that 14 is a representation of 7, and then I'm going to use the quotient of 2, and I'm going to add to that remainder, which is the remainder of 0. On the other equation, when we had a equal 15 and b equals 7, we're going to say that the quotient is equal to 15 divided by 7, which is also 2, and that the remainder is going to be 15 mod 7, which is going to be a remainder of 1. So this will also give me 15 is equal to 7. This time my quotient is still 2, but now my remainder is 1. Let's try this with something a little bit more difficult. A equal to 614, b is going to equal 32. So that means that my q value is going to equal 614 divided by 32, and my remainder is going to equal 614 mod 32. One of the best ways that I can do this calculation is a calculator. If I pull up a calculator in the Windows operating system, I can do 614 divided by 32 is going to give me 19. So we'll put that number down, 19. But how do I find out what this remainder is? There's another view on a Windows calculator. If I go into the programming view, there is this mod operation right here. So now I can do 614, and if I press the mod function and I do 32, it will tell me what the remainder is. And this is a remainder of 6, so let me add that in. So we'll see that 614 can be written as 32. My q value is 19, plus I have a remainder of 6. The mod operator tells us what the remainder of a division is. So if I had an a value of 4 and I had a b value of 2, That means that I would take my A value and I would divide it by my B value, and 2 goes into 4 2 times, and if 2 times 2 is 4, if I subtract that, that gives me 0, which means here my remainder is 0. But let's say that I had an A value of 5 and a B value of 2. This time I'm going to take a 5 and I'm going to divide it by 2. Well, 2 goes into 5 2 times. 2 times 2 is 4. If I subtract that, that gives me 1. This means that what is left over is my remainder of 0. So we're going to find out that the remainder is always going to be between 0 and 1 less than the number that I am modding it by. So let's say, for instance, that I was doing a mod 3. The remainder of a mod 3 is going to be somewhere between 0 and 2. If I was doing a mod 4, the remainder is going to be somewhere between 0 and 3, which would be 1 less than 4. If I was doing a mod 16, my remainder is going to be somewhere between 0 and 15. Let's come back to our mod 2 for just a minute. Let's say, for instance, that I was trying to do 2 into 6. If I were to say 2 goes into 2, 2 goes into 6 2 times, well, that would give me a 4. And if I subtract 4 from 6, this gives me a 2. The fact that I have 2 left over and I was dividing it by 2 originally tells me that I didn't go far enough. My remainder is too large. And so if I had done 2 goes into 6 3 times, then 2 times 3 is 6, and I would have subtracted the 6 and it would give me a 0 left over, which tells me that when I am doing a mod 2, my remainder is going to have to be either 0 or 1. My remainder cannot be 2. If my remainder is 2, that means that I didn't have a large enough quotient. So keeping this in mind in what the mod operator means, let's try one more of them. What if I said a negative 17, A is a negative 17, and B is 3. Let's see if I can represent a negative 17 by some value 3 multiplied by a quotient plus some remainder r. Well, we said that we're going to find the quotient by taking a negative 17 and dividing it by 3, and I'm going to find the remainder by taking a negative 17 and doing the mod. So when I do this, my brain is telling me that 3 goes into a negative 17 5 times. And so I would be inclined to say that this is going to give me a negative 5. So if it is giving me a negative 5, and then I do the mod operator between a negative 17 and 3, if this is going to give me a negative 15, the only way that I can get from a negative 15 to a negative 17 would be to have a negative 2, right? Negative 15 plus a negative 2 is a negative 17. And this would say that my remainder is a negative 2. But we have already determined that the definition of a remainder is that it must be between 0 and the number that I am dividing by, which means that my remainder here must be somewhere. Because I am dividing by 3, it would have to be between 0 and a positive 2. Well, a negative 2 is not between 0 and a positive 2. When we're dealing with negatives and our division, things get a little bit different. So let me see if I can get a clear understanding of what's going on here. Let's say that I took a positive 17 and I divided it by 3. This number would give me 5. I know that 3 times 5 is 15. And then if I subtract that 15, it is going to give me 2. I would have 2 left over. And this was my expectation, that I had a remainder of 2. But what happens if I am doing 3 divided by a negative 17? Well, once again, if I put a 5 here, 3 times 5 is 15. If I subtract these two numbers, I'm going to end up with a negative 32, and this does not work. All right, so let's try it again. We're going to take 3 and we're going to divide it into a negative 17. Well, I can tell that the positive 5 didn't work, so now I'm going to try negative 5. A negative 5 times 3 is a negative 15. But it said that I had to subtract that, which means that it's going to trip this to be positive. So a negative 17 plus 15 is going to give me a negative 2, which means that I have a remainder of a negative 2. But we've already said that I cannot have a negative remainder for a modulus operator. My remainder has to be between 0 and 1 less of the value that I am dividing it by, which then means that my remainder must be between 0 and 2 if I am doing a mod of 3. So we're going to try it one more time. I'm going to take 3 and I'm going to divide it into a negative 17. And this time, instead of doing a negative 5, I'm going to do a negative 6. I'm going to go one more than the 5. This is going to give me a negative 18. 6 times 3 is 18. I'm going to subtract that negative number, which means I'm going to end up adding a negative 17 to a positive 18, which is going to give me a positive 1. So my remainder is going to be a positive 1. And this remainder is definitely within the tolerable limits of 0 to 2. So if I look back at the problem that I was trying to solve originally, which was a is equal to a negative 17 and b is equal to 3, we're going to find out that this is the only quotient that is going to allow my remainder to be a positive 1, which means that a negative 17 can be represented as a positive 3 multiplied by the quotient. Well, here is my quotient, which is a negative 6. And then I'm going to add my remainder, which is 1. If I wanted to verify this, I would say a negative 17 is equal to, well, 3 times a negative 6 is a negative 18. A negative 18 plus 1 is indeed a negative 17. And so I can tell that these two values are indeed the same. So when I'm applying the division algorithm with positive integers a and b, it works out much as I would expect it to do. But if my a value or my b value for that matter are negative, I just have to pay attention to what my remainder is generating.